Hello and welcome back to my channel. So today's topic will be about multiplication, but before I begin, I'd like to address the fact that the audio quality on the last few videos hasn't been that great. So having now discovered the fact that I can actually clean up the audio with the tools I already have, I've endeavoured to do that for this video, so hopefully you aren't getting deafened in your left ear and you haven't got to, suddenly strain to hear me. So that's what I hope to do from now on. Multiplication isn't something you can really do in a Commodore 64 without having to write code for it. If you're using BASIC on the Commodore 64, there are routines that you can just type in and you'll get the result come up straight away. The 6502 doesn't contain a dedicated routine or set of commands to do multiplication with. If you've used potentially other processors like DSPs or much newer processors, you've probably got some sort of multiply command. Well, this doesn't have anything like that. What you have to do is take it in stages and divide that task up. Before I attempted to write any code, I wanted to make sure I understood the theory, which would make writing the code a lot easier. At some point, I intend to introduce more interesting concepts than what I've been doing so far, but whenever there's a mathematical theory involved, what I like to do is just write down the results until I'm happy that I understand the process, and then I can write code for it. Okay, so basically this is a multiplication of two nibbles. Now, the reason we're sticking to 4 bits, if you get any number that's above 255, you need to start thinking about adding more steps into this process and concatenating, or certainly adding together numbers to create 16-bit numbers, and that can get a little bit difficult to manage, and I feel that's a little bit beyond the scope of this video, but I'm going to keep it simple for now. This is us multiplying 11 by 3, and you can see I've written the binary numbers there, and that's the result. We will take the number to be multiplied and the number we are multiplying it by. We look at each digit as we go along, and if the first digit contains a 1, then we're going to add this to the result, and if it's a 0, we are not. What you're actually doing is doubling the number every single step, and then you decide whether you're going to add that or not based on whether the position is a 1 or a 0. So in this particular instance, we start at 0, and we're going to consider adding 11 to it. As the first number is a 1, we add that 11. And we look at the second number, and that's also a 1. So we're going to add 22 to this. And the next number would be 44. But as the third number is a 0, we're not going to add that. The next number is 88, but the fourth number is a 0, and we're not going to add that. We start with 11, we add 22, and we end up with 33. In another example, if we wanted to times 15 by 15, which is effectively all the ones, we'd end up with 225. So we would add 15, 30, 60, and 120 to get 225. So this is a simple program which will multiply 15 by 15. We have a variable called multiplier, which is the a in a times b, multiplicand, which is the b in a times b. We have control bit, shifted byte, step number, and result. What these do, these are temporary storage areas for the numbers as we manipulate them. Result is a variable which is added to every time we carry out the loop. And step number just records how many times we've done the process, because we want to do this 4 times. Something else I'll point out is that if we want to multiply larger numbers than this, we have to start thinking about maintaining 16-bit variables and doing more stages to this calculation, which I wasn't too keen on doing. So for now, I'm not going to go there, but managing 16-bit numbers is something that I covered in a previous video. We're going to load the accumulator with 15 decimal. We're going to store that in multiplier, and we're going to store that in shifted byte. We also do the same thing for multiplicand and control bit. This loop here is run 4 times because there's 4 bits that we're evaluating. So we start with a clear carry flag. Don't forget, if you're doing an addition, you should be clearing a carry flag. The program might not work reliably if you don't do this. Certainly, I had problems when I first wrote this bit of code because I forgot to do clear carry flag and had some strange results that didn't seem right. We load the accumulate with control bit, which contains 15, and we do a logical shift right. What this does, it moves the entire number to the right or set the carry flag depending on whether the bit we lost, the LSB, was a 1 or a 0. And if it is a 1 or a 0, we'll then branch to determine whether or not we should add what is in shifted byte to the number we've already got there. Shifted byte will contain 15, then it'd be 30, then it'd be 60, then it'd be 120 as we go through each iteration of the loop. if the result is a 1 each time, we're going to add initially 15, then we're going to add 30 to it, then we're going to add 60 to it, and then we're going to add 120 to it because all bits were a 1. If any of those bits had been a 0, we wouldn't add the number and we would then just prepare for the next. So that's what this prep next does. So we clear the carry flag again. We load shifted byte because that's going to be the 15, 30, 60, 120, and we add it to what's already there. So we start with 0, we add 15 to it. On the next iteration, we add 30 to 15, which is going to be 45, and so on and so forth. Once we've done that, we go to prep next, and this is going to prepare the next numbers for the next iteration. So shifted byte gets shifted left, and that's just basically doubling the number for the next number you're going to add. So the next thing we do is we compare step number with 3. If step number has reached 3, then we are on our 4th iteration, and there's really nothing left to do. That's the end of our multiplication. The reason it's done 4 times is because we're only evaluating the low nibble of each byte. So once we've got to 3, we just branch if equal and get to end and the program finishes. Well, I hope you can see this okay. What I intend to demonstrate is you'll see control bit going one way and shifted byte going another until step number has reached 3 and we do our final addition. You can see it's loading the various variables with 15 here. So at this point, this is the point where we have done the logical shift right of control bit. We've lost the LSB. We're going to branch shift the bit that we just removed was a 1. In every case, it's going to be a 1 every single time we run this program because we're evaluating 1, 1, 1, 1. Had it been a 0 in any of those, then we'd have branched to carry clear to address 0832. So we won't be doing that on this one. But this code is scalable, so if we did feed another value into this, then we'd be branching to not adding to what we just added to, if that makes sense. And you can see now result contains 15. On the next pass, we're going to add 30 to that to get 45. On the next pass, we'll add 60. On the next pass, we add 120. And there we go. Basically the end of the program. We now compare to 3 and finish the program there. Branch if equals to 0846, which is where it's gone. I'll just scroll off the bottom there. And that's the end of the program. So there's one more thing I meant to add is that I had intended to write some code that outputted to the screen the decimal value, and I discovered this to be very time consuming and didn't finish it. So what I'm going to do in one of my future videos is make that its own subject. So that's the end of the program. Thanks for watching. Cheers.